This is the video for section 10-1 and on series and sequences and sigma notation. So we're going to start with some definitions. If you just have a list of numbers, it's called a sequence. And so an example of a sequence would be, let's just say 2, 4, 6, 8. And then we can talk about if this sequence ends or if it keeps going. Each separate number is a term, and the notation that you would use, if I have a sequence 2, 4, 6, 8, 8 is the fourth term in my sequence. And so we would use the notation A with the little subscript 4 equals 8. And that's a notation we're going to use. Sequences with a limited number of terms are called finite sequences. So if this sequence that I had above ended at, let's say, 20, that would be a finite sequence. If it goes on forever, if the ... and it just keeps going and you keep adding to and adding to, that's an infinite sequence. I'm going to take the S off of that one. So there's two different formulas to use to describe a sequence. Naturally, when we start describing a sequence, we use a recursive process. We talk about how would I get the next number. And so if I was going to describe this sequence to someone, I would say to get the next number you would add 2. That process is a recursive formula. And I'll show you another example when we do example number 1. And then what we have spent a lot of time doing in mathematics is use a rule that uses the term number. So when I set up a linear equation for a sequence, I'm using the term number, and that's called an explicit formula. So we'll do an example of both of those when we look at example 1. So here's example 1. The first thing it asks us to do is find the next 4 terms of the sequence. So we have to figure out the pattern. 3, -1, -4, -9. We can see that it's going down. So we just have to figure out what number would I subtract from 3 to get -1, and that would be negative. I would subtract 4. -1 minus 4 would be -5. So if I kept doing that, -9 minus 4 is -13, -17, -21, and -25. If I want to practice a recursive formula, the way the recursive formula works is you have A sub n, and this stands for your next number in your sequence. And the way you find it is you use the previous number, and then you just write your rule, which in this case would be -4. So again, this is your A sub n. To find your next number, you take A sub n minus 1, which means the number in front of A sub n, or the previous number, and subtract 4. An explicit formula to find A sub n, I have to figure out when I use 1, and I plug it into a formula, I want the answer to be 3. So the 3 is the first term, so I want n to equal 1 for the first term. So I know that I'm subtracting 4, so I know that I'm going to multiply 1 by -4, which would give me -4. And what would I have to add to -4 to get 3? And -4 plus 7 is 3. So for this example, it would be -4 times whatever term I have, which I'm going to call n, plus 7. So for example, let's say I want to find the third term. So the third term would equal -4 times 3 plus 7. which is negative 12, plus 7, which is negative 5. If I use my recursive formula to find the third term, I need to take the second term and subtract 4. The second term in this example is negative 1 minus 4 would give me negative 5. So I can use both formulas to find the negative 5, which is the third term. The power for explicit formulas, if now they ask you for the 100th term, you're definitely going to want to use an explicit formula, because to find the 100th term, I would have to find the 99th term if I was using recursive. The power with recursive is usually when someone describes a pattern, they see it as a recursive formula. So all of these have an example and a practice, so if you want to pause the video and try the practice on your own, you're welcome to. So you'd pause it now. And so this question asks us to find the next 4 terms. We can see that I am subtracting 3 and then subtracting 5 and then subtracting 7. So I'm still subtracting a number, but I'm not subtracting the same number every time. So to find the next one, I would want to subtract 9. So 3 minus 9 is going to be negative 6. And then I would want to subtract 11. Negative 6 minus 11 is negative 17. Subtract 13, which would give me negative 30. Subtract 15, which would give me negative 45. So the next 4 terms would be here. So example 2 gives us some practice with some explicit formulas. We have a sub n equals n cubed plus 1, and they want us to find, it says the next 4 terms, but the first 4 terms. So a sub 1, I just want to substitute 1 in for n, so we've done lots of practice with this. 1 cubed, which is 1 plus 1 is 2. A sub 2 is 2 cubed plus 1, so 8 plus 1 is 9. Third term would be 3 cubed plus 1, 27 plus 1 is 28. And the fourth term is 4 cubed, which is 64, plus 1 is 65. So if I list out this as a sequence, it would be 2, 9, 28, 65. And it doesn't tell me that the sequence is finite, so I'm going to assume it's infinite and put dot, 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 or the ellipses to show that the sequence continues. And if you want to try the practice on your own, pause the video. Practice 2, find the next 4 terms of this sequence. This time we're multiplying by, or dividing, depending on how you want to look at this, dividing by 3 or multiplying by 3. So I prefer to multiply by a third because it gets easier as I get into fractions. Multiply by a third, get 27 times a third, 9. Multiply by a third, so the next 4 terms, if I multiply 3 by a third, that would give me 1. 1 times a third is 1/3. 1/3 times a third is 1/9, and 1/27. Final example on the page, recursively defined sequences. These are going to be the ones that use the term before. This pattern cannot start until n is greater than or equal to 2. So it tells me, as most recursive formulas do, and I should have included that in the notes up above, it tells you your first term. So we should have said a sub 1 equals 3 in that example above, because you always need a starting value for a recursive formula. In this recursive formula, it tells us that the first term is 3. So if I want to find the second term, and that's the first, I have the first term, so the first term I can use a formula to find is the second term, and that's why n has to be greater than or equal to 2 to use this formula. So if n is 2, it says 3 times the previous term, so 3 times the first term, minus n, and n would be 2, plus 2. And my first term is equal to 3, so 3 times 3 is 9, minus 2 is 7, plus 2 would be 9. To find the third term, I would take 3 times, and I want to plug the second term in, which is 9, minus 3 plus 2. So 27 minus 3 is 24, plus 2 would be 26. To find the fourth term, it's 3 times the third term, which happens to be 26, minus 4, because n is 4, plus 2. 3 times 26, I know 3 times 25 is 75, plus 3 is 78, minus 4 is 74, plus 2 is 76. And it said find the fourth term recursively, and so the fourth term would be equal to 76. But notice that in order to find the fourth term, first I had to find the third term. Well, first I had to find the second term, then the third term, then I could find the fourth term. Here's one for you to practice. Find the fifth term of the recursively defined sequence when the first term is equal to 28. And the recursive formula is to find the next term, you take half of your previous term and then add 4. So to find the first term, I'm going to find the fifth term, I'm going to find the second term. So that's going to be half of 28, because I'm going to plug 2 minus 1 would be my first term, so I want to plug my first term in here, plus 4. So half of 28 is 14, plus 4 is 18. To find the third term, I'm going to take half of 18 plus 4. Half of 18 is 9, plus 4 is 13. The fourth term, half of 13, oops, it's a 2, is 6.5, plus 4 would give me 10.5. Math is getting a little trickier. Half of 10.5 is going to be 5.25, plus 4 would be 9.25. So my fifth term is 9.25, or 9 1/4. For example 4, some sequences that go on forever actually get closer and closer to a given number, and that's called converging on that number. Some sequences just go towards infinity and just keep getting bigger or keep getting smaller. So if I was adding 1, that would be a divergent sequence. It's going to keep growing and keep growing. If I'm taking a number and I'm cutting it in half, 10 and then 5 and 2.5 and 1.25, my answer is going to get smaller and smaller and smaller and smaller, and it's going to get closer and closer to 0. So a sequence that converges if as the term number increases, the term value approaches a number, or this sentence, says a sequence converges if as the term number increases, the term value approaches a number. And so that would be the one I said where I was cutting in half, it gets closer and closer to 0. And that sequence has a limit, which we studied in chapter 1. So here we want to take this sequence, and it says to find the nth term, you have negative 4,000 times 1/4 to the nth. So we want to figure out, is this getting closer and closer to a number, or is it just getting smaller and smaller and smaller? I think maybe the easiest on this would be to look at a graph. We know this is an exponential function. It has a starting value of negative 4,000, and you're multiplying by 1/4. So it's a fourth of a 4,000 is going to be a negative 1,000. So this is similar to the example that I gave. You're going to always take a fourth of the previous number. So my first term, if I plug 1 in here, negative 4,000 times negative 1/4. This is 10.1 notes, page 2, and the concept that we're going to start with is whether a sequence is convergent or divergent. If a sequence is convergent, that means as you plug in more and more values into the sequence, that the term values approach the same exact number. This is similar to a concept that we learned in chapter 1. That means if a sequence that converges has a limit, where if the sequence just gets larger and larger and doesn't approach a value, then we would say that the sequence is divergent. And so our first example here, we have a sub n equals a negative 4,000 times negative 1/4 to the nth power. And we want to decide, is this a convergent or a divergent sequence? So if you plug in negative 1 for n, if you plug in 1 for n, that would be negative 4,000 multiplied by negative 1/4, which would equal 1,000. If you plug in 2, then you're going to be multiplying negative 4,000 by negative 1/4 twice, which means I would just be multiplying 1,000 by negative 1/4. If we look at this recursively, to get the next value in the sequence, I would multiply the previous value by negative 1/4. So that would be negative 250. And I could set this up, take negative 250 and multiply that by negative 1/4 or negative 0.25 and get positive 62.5. And find the fourth term, multiply by negative 0.25 and get negative 15.625. If I continue, you can see that the values oscillate between positive and negative. So negative 15, positive 3.9, negative 0.97, positive 0.24. But we can also see that even though the values are going back and forth between positive and negative, the values are getting small. And let me just press enter a whole bunch of times here. They're getting really, really small. So I think this was negative 15. 62.5 divided by 4, negative 15.625. So we can see if we looked at a graph of this concept, like we'd start at 1,000, then negative 250, then 62, then negative 15. If we looked at a graph, we would say that even though this is above the x-axis, below, that the values would get smaller and smaller. And so we would say that this is convergent, or the series converges, sequence converges. I also did put this in the graphing window, and you really can't see. I can see if I trace along here and put in different values. 1, 2. I can see the values that I saw, but you can't really see on the calculator. I also tried it on the Inspire, and it ended up connecting the values. I also tried graphing it on the Inspire, and it connected the points, which makes the graph look really, really weird. So it's hard to see these on the graph. You might want to try going to the table or using a recursive idea like I did with the other calculator. And once you have the calculator or the table, you can scroll down and you can see that this is approaching 0. So let's try the second one says practice, but let's try it as an example. We want to plug in values again, and this sequence is a sub n equals negative 2 to the nth power divided by 2. So if we plug in 1, we have negative 2 to the first power, which is negative 2 divided by 2 would be negative 1. And if we plug in 2, negative 2 to the second power is 4 divided by 2 is 2. Plug in 3, negative 2 to the third power is negative 8 divided by 2 is negative 4. And we can start to see a pattern develop and understanding recursively what's going on. We're multiplying by negative 2 every time. So this would be 8. So again, our values are negative and then positive and then negative. They're alternating signs, but they're getting bigger every single time. So this is, it is diverging. It diverges. The sequence does not approach, does not have a limit, so we would say it's divergent. A huge concept in this chapter is the difference between a sequence and a series. A sequence is a list of numbers, and that's what we've been doing so far. So up here, if I would have listed my numbers, negative 1, 2, negative 4, 8. That would be a sequence. A series is the sum of all the terms in a sequence. So this is you add your terms together. So if it says partial sum, you're taking part of the sequence and adding those terms together. So in example 5, where they say find the fifth partial sum, they want you to find the first 5 terms of the sequence and add those together, and that would be the fifth partial sum. So if I plug in 1, 1 to the second power is 1 minus 3 is negative 2. If I plug in 2, 2 to the second power is 4 minus 3 is 1. Plug in 3 to find the third term, and I get 3 squared is 9 minus 3 is 6. Plug in 4, 4 squared is 16 minus 3, which would be 13. And plug in 5, 5 squared is 25 minus 3 would be 22. So the notation is you use an S and put a subscript of 5 to mean that the sum of the first 5 terms. So negative 2 plus 1 plus 6 plus 13 plus 22. So 13 plus 22 would be 35, 41, 42 minus 2, and the sum of the first 5 terms would be 40. If you want to try the next one on your own, pause the video. I'm going to find the first 4 terms, then add those together. Oops, I did not mean to use S's. That would mean the sum. I want the first 4 terms. So if you substitute in 1, 6 divided by 2 to the first power would be 6 divided by 2, which is 3. 6 divided by 2 to the second power is 6 divided by 4, which is 1.5. If I plug in 3, that would be 6 divided by 8, which is 3/4, which is 0.75. And the 2 to the fourth power is 16, so 6 divided by 16 is 3/8, which is 3.375. And I think I'm going to use my calculator to add these up. So that would be 3 plus 1.5 plus 0.75 plus 0.375. And the sum, this is when I want to use the S, meaning I'm adding these 4 terms, would be 5.625. This next demo, if you want to watch this online in your textbook, you can go to the online textbook, and on page 594 they do this exact problem. Sigma, uppercase sigma, Greek letter sigma, is the same as sum, and it's used when you want to take the sum of a series. The number down here in this case is a 1. This is the starting place. You don't always have to, if you use sigma notation, you don't have to start at 1. And the number that's on top is when you stop. So this is asking us to plug in 1 into the expression n squared minus 1 and add that together with plugging in 2 and 3 and 4. So this is going to equal, if I substitute in 1 squared minus 1, I'll find that value, and I want to add that together with 2 squared minus 2, and add that together with 3 squared minus 3, added together with 4 squared minus 4. So I'm just plugging each of those values into the expression n squared minus n, starting at 1 and stopping at 4. So I want to figure out what that is. 1 squared minus 1, that's 0. 4 minus 2 is 2. 9 minus 3 is 6. 16 minus 4 is 12. So 8 plus 12 would be 20. So sigma notation from 1 to 4 of n squared minus n would equal 20. One last example, and again you're welcome to pause it and try it on your own, is from 1 to 5, find the sum of n cubed minus 2. So we're going to plug in all those values again. So I'm going to have 1 cubed minus 2 plus 2 cubed minus 2 plus 3 cubed minus 2 plus 4 cubed minus 2 plus 5 cubed minus 2. And I know I want to stop at 5 because there's a 5 at the top of the sigma notation. 1 squared minus 1 squared minus 2 would be negative 1. 8 minus 2 is 6. 27 minus 2 is 25. 64 minus 2 is 62. And 125 minus 2 is 123. I know that negative 1 plus 6 is 5, plus 25 is 30, plus 62 is 92. So I need to add 92 to 123. It's going to be 8 short of adding 100. So 223 minus 8 would be 215. So my answer would be 215 for this problem.